Good day, young scientists. Let me start with a question. Have you ever noticed how you feel lighter when you step into a swimming pool? Or why massive ships made of iron float while a tiny iron nail sinks instantly? The man who answered this question thousands of years ago was none other than Archimedes, a brilliant Greek scientist who once ran through the streets shouting, "Eureka!" after discovering a law that changed physics forever. Here's what he found: when a body is submerged in water, it experiences an upward force. This upward push is known as buoyant force. The more water the object displaces, the stronger this upward force becomes. As you'll see in the diagram, Archimedes observed that when an object is dipped in water, the water level rises, meaning the displaced water has weight. And the object seems lighter by exactly that amount. That observation became the foundation of Archimedes' Principle, the rule that governs why things float or sink. Now that we know the story, let's define the principle clearly. Archimedes' Principle states, when a body is partially or fully immersed in a fluid, it experiences an upward force equal to the weight of the fluid displaced by it. This upward force is called the buoyant force, and we denote it as F sub b mathematically. F sub b equals rho times g times v, where rho is the density of the fluid, g is the acceleration due to gravity, and v is the volume of the fluid displaced. The buoyant force always acts vertically upward through the center of buoyancy, which is the point through which the force appears to act. Imagine holding a ball underwater. The moment you let go, it rushes up. That's buoyant force in action, the fluid pushing back with a force equal to the weight of the displaced liquid. Now let's think about what affects buoyant force. It depends mainly on two things: the density of the fluid and the volume of fluid displaced. Denser fluids like mercury or salt water exert greater buoyant force than lighter fluids like oil or air. Similarly, an object that displaces a larger volume of fluid experiences a greater upward thrust. Here's the interesting part: it's not just about material, but also about shape. A solid iron cube sinks because it displaces little water compared to its weight. But an iron ship, though massive, is hollow and displaces a huge volume of water, which provides a buoyant force strong enough to keep it afloat. In the diagram, compare the cube and the ship. The cube sinks straight down, while the ship floats because it balances its weight with the buoyant force. That's why design and density together decide what floats and what doesn't. Let's test the principle with a quick numerical example. Suppose we have a cube of volume 0.02 cubic meters floating in water. The density of water is 1000 kilograms per cubic meter. The weight of the displaced water equals rho times g times v. That's 1000 multiplied by 9.8 multiplied by 0.02, which gives 196 newtons. That means the buoyant force equals 196 newtons. If the cube's own weight is less than 196 newtons, it floats. If it's greater, it sinks. So, buoyancy is basically nature's balancing act. If the upward push of the water matches your weight, you float. Otherwise, you go under. You can see this clearly in the diagram: one cube floating because the forces are balanced, another sinking because gravity wins. Let's wrap up what we've learned. Archimedes' principle tells us that the buoyant force on a body immersed in a fluid is equal to the weight of the fluid displaced. The formula is F sub b equals rho times g times v. This explains why some objects float, some sink, and some stay suspended. When the weight of the object equals the buoyant force, it floats in equilibrium. From ships and submarines to hot air balloons and hydrometers, this principle forms the backbone of all buoyancy-related technology. So, next time you see a massive cruise ship gliding smoothly or an iceberg floating effortlessly, you'll know It's all thanks to Archimedes' Eureka moment. I hope you enjoyed exploring this principle as much as Archimedes did. See you in the next session with another fascinating journey into the world of physics.